So last class we left off, we were talking about direct proportionality. We looked at power functions, and we stuck with basic exponents, with whole number exponents mostly. But I want to just point out that with power functions, you can use any number as an exponent, any number that fits the situation. It doesn't have to be a whole number. Doesn't have to be positive or negative. It can be any variable or any value that you want. It doesn't even have to be rational. You could have an exponent of pi or e or whatever you'd like. The differentiator, though, what makes it a power function over a polynomial, or makes it a power function over an exponential function, is that the variable is in the base. With an exponential function, the variable is the exponent. With a power function, the variable is the base. So what we're going to start by looking at today is the effect that the exponent has on the function itself. We know that, first of all, if p is 0, anything to the 0 power is 1, and so our function becomes a constant function. We have f of x equals k, right here. Okay, p is 1, or p is 0, then x to the 0 is 1, and we have f of x equals k. That's just a horizontal line. If p is 1, x to the 1 is just x, and we have, for our function, k times x, which is a linear function. In other cases, we want to look at what happens, what the values of p will do to affect the graph. So let's start with p as positive numbers. The beauty of using positive integers, we're going to stick with just integers to start, is that when we have power functions with positive integers, we have nice symmetric graphs. We have basically polynomials that are not shifted, that are not changed in any way. They pass through the origin, and they provide us with a nice perfect symmetry, either even symmetry or odd symmetry. Of course, we get even symmetry if p is even. We get odd symmetry if p is odd. So, for instance, if I had a function, there we go. If I had a power function where the exponent was, say, 4, and it doesn't really matter what k is at this point. Suppose our exponent is 4. Then f of negative x is equal to k times negative x to the 4th. And when we raise a negative to an even power, we get a positive number. This is the demonstration that a even positive integer, well, actually an even negative integer as well, but an even integer for a power gives us even symmetry. In other words, it is symmetric over the y-axis. So if I were to reflect it over the y-axis, it would lay on top of itself, essentially. The other option with positive integers, or even with negative integers, is that p could be an odd number. If p is an odd number, let's just go to 5, then when I take and evaluate f of negative x and raise negative x to the 5th, I get a negative, because a negative raised to an odd power is negative. So I have negative kx to the 5th. And so f of negative x equals the opposite of f of x. This is what we call odd symmetry. And we say it's symmetric about the origin, but that's kind of hard to picture. And so I always look at it as a reflection over the x-axis is the same as a reflection over the y-axis. So you could reflect over the x-axis, you get the same as if you reflect over the y-axis, or you could do both reflections, reflect over the x and y-axis, and it would get you back to where you started. So we covered this a little bit back in Chapter 3. I just wanted to see kind of how it applies to power functions. So if p is an integer, then your power function is always going to have some symmetry, either even or odd symmetry. Because if it's a whole number, positive or negative, then it has to be even or odd. If it's even or odd, then it has even or odd symmetry. So it's always going to have some of that symmetry to it if p is an integer. Just as a reminder, p doesn't have to be an integer. But when it is, we have these special cases. So the graphs were meant to be split up a little bit in the notes, but they kind of both just popped at the end of the section. So on the left side, we're going to look at just a couple of examples where p is even integers or positive integers, and we'll see what that even symmetry looks like. And this is going to this application here is going to kind of spread into our polynomials real easily. So if we start with y equals x squared, we know that we have a parabola with a vertex at the origin. If we have a power function that has a positive exponent, it's always going to include the origin. The reason is because with a power function, there's no constant being added out here that would shift it up or down that would give you a new y-intercept. Whenever you plug in 0 for x, you're going to get 0 out for y. So that origin is always going to show up. If it's a negative integer, then it's always going to have an asymptote, and we'll get to that in a little bit. So we know that with or hopefully we know that with quadratic functions, with the parabola, we have a nice steady incline as we go left and right. We kind of covered this back in Chapter 3, and it's something we should have seen in Algebra 2 and worked quite extensively with. So here's a nice positive even integer. Now, if I were to raise that exponent a little bit, but keep a even number, so we'll skip up to x to the fourth. As I mentioned, we're still going to have that intercept at the, or that intersection at the origin. It's always going to be there. The difference is what's happening pretty much everywhere else. It also has these 2 points in common, because when I raise 1 to the fourth power, I still get 1. The question is, if I plug in numbers in this range here, what's the difference between x squared and x to the fourth? So in other words, suppose I plugged in 1/2. Which one's larger, 1/2 squared or 1/2 to the fourth. Which one's larger? 1/2 squared is larger. Okay? 1/2 squared is just 1/4. 1/2 to the fourth is 1/16. When you raise numbers that are between 0 and plus or minus 1 to a higher power, they get smaller. So for x to the fourth, these values in here are going to be below x squared. And as that exponent climbs, if it were x to the sixth or x to the eighth, it would get even lower. And so the higher power you have there, the flatter it gets in that region there. But then when x is greater than 1, okay, say 2 or 3 or whatever, obviously the higher power is going to make it bigger. And so outside that domain, x to the fourth is going to rise much faster than x squared. And so we have this kind of compression between -1 and 1. It gets squished down to the x-axis, but outside it gets pulled upwards. And as the power gets higher but stays even, it gets stretched even further. That difference becomes more and more drastic. Let's look at what happens when p is odd. So suppose we have x to the third. Now we're just sticking with k being 1 here for convenience. Obviously it could be another number, but we're going to stick with 1 for convenience. So again, if p is positive, our graph has to include the origin. And when x is positive, x to the third is going to be positive. So again, we're going to include that point 1, 1. And it's going to continue to increase from there. It's going to increase a little bit faster than x squared, but not quite as fast as x to the fourth. However, when x is negative, we get negative values out. If x is -1, we get a -1. And so our graph is going to decrease on this side in a way that is symmetric to the opposite side, to the positive side. Of course, you could plug in more values for x to see what values for y would come out to make this really accurate. But that's not really the point right now. We just want to look at the shape. And this shape is going to help us a lot. This concept is going to help us a lot when we get to graphing polynomials. But let's throw one more up there. Let's look at an x to the fifth. And we're going to see that the relationship between y equals x to the fifth and y equals x cubed is very similar to the relationship between y equals x squared and y equals x to the fourth. You still have the same intercepts there. You still have 0, 0. You're still going to have 1, 1. And you're going to have -1, -1 because you have that odd power. But because that power is increased, in between 0 and 1, when you raise those fractional values to a higher power, you get smaller numbers. And so it's a little hard to see, but the x to the fifth is going to be below the x to the third in between 0 and 1. It's not quite as drastic as I just drew it. I just drew it that way so you could see it. And same on the other side. Okay, it's going to be just inside that green area. And then it's going to climb even faster than x to the fourth does because it's got a higher power. And so raising that power tightens it up in between 0 and 1 and 0 and negative 1, but it stretches it out outside those bounds. Are there any questions on the positive integers? Okay, so we'll get to non-integers in a little while. Let's look at negative integers. So the difference with negative integers, and we're going to graph them right next to it, is let's start with odd. We're going to start with the most natural one. Y equals x to the negative 1. And I personally think it's more helpful to look at this as y equals 1 over x. Because when you look at it like that, you see the asymptotes a little more readily. You see that I can't put a 0 in for x. For me, that's easier to see in this format than it is in the negative exponent format. So it might be helpful to remember whenever p is negative, x can't equal 0. And if x can't be 0, then y is not going to be 0. There's no way you're going to get a 0 out of this fraction. The only way you could get a 0 out of the fraction is if the numerator is 0. And if the numerator is 0, well, that's your k. K would have to be 0. And then it's not really a power function anymore. It's just y equals 0. And so we have asymptotes for our graph. Let's see. On the axes, so that y can't be 0 and x can't be 0. I find that the most helpful way to look at this graph, or to think about what points are on this graph, are to consider the fact that if y equals 1 over x, x times y has to equal 1. If x times y has to equal 1, then you have a bunch of coordinates so that when you multiply the two values together, you get 1. So that would include points like 1, 1, and 1/2, 2, and 2, 1/2, and 1/3, 3, and 3, 1/3, and so on. And so we would have points that form a shape we call a hyperbola. And they're going to get successively closer to the x and y axes without actually touching them. But we also have the points -1, -1, and -1/2, 2, and -2, -1/2, and -1/3, -3, and -3, -1/3, because all of those products are also going to give you a positive 1. Does everybody understand how I got that graph? All right, take a second and before we go into different powers, consider how you would graph y equals 6 over x, or 6x to the negative 1. Take a couple minutes and just think about what points would be on that graph. I'll let you think about it for a few seconds and we'll go over it together. Okay, who could give me a point that would be on y equals 6 times x to the negative 1? One 6 would be one. What else? I'm sorry? 6 1. Okay. Remember, this is the same as x times y equals 6. What other pairs can we put up there? 2 3. 3 2. All of those are going to be on the graph. And of course, the negative ones are going to be there too. Negative 1, negative 6. Negative 6, negative 1. Negative 2, negative 3. And so what we get if we raise k in that case is we get numbers that are a little further, we get points that are a little further out here, and it pulls away from the origin a little bit. Kind of stretches it out. Okay? All right. So that was just a little critical thinking exercise. Let's look at what happens if we raise p to the next odd integer. So we have y equals x to the negative 3, or 1 over x cubed, or x cubed times y equals 1, which is a perfectly accurate way of looking at it. Not quite as convenient as x times y equals 1, because then you got to find a number that when you cube it and multiply it by y, you get 1. But that's not really the point of looking at this. The point is to consider what happens as that increases in view of what we learned on the positive side. So if we think about it, 1 1 is still going to be on x cubed y equals 1, or y equals 1 over x cubed. And no matter what odd power we put there, we're going to get that point. But 2 1/2 and 1/2 2 aren't going to be there. If we think about it, if I put in 1/2 for x, when I cube it, what is 1/2 cubed? 1 over 8. And so y has to equal 8. And so between 0 and 1, well, if we put in 1/2, we get 8. Before we got 2. So now we have this point right here, which is directly above this point. We also have 8 1/2. No, I'm sorry, we don't have 8 1/2. That's a terrible way of looking at that. What happens if y is 1/2? If y is 1/2, x cubed has to equal 2. And so when we take the cube root, we get x equals the cube root of 2, which is ridiculously small. And so out here, if we put in a y of 1/2, we have to get a very small number. It's a little bigger than 1, but it's much smaller than 2. And so we see the same thing. We see not the same thing. We actually kind of see the inverse happening. Before, between 0 and 1, we got closer to the x-axis. Now we're getting a little further away. It's actually stretching out between 0 and 1. And from 1 on, it gets smaller. And the reason is because we're not looking at x cubed, we're looking at the reciprocal of x cubed. So when x cubed gets bigger, 1 over x cubed gets smaller. When x cubed gets smaller, 1 over x cubed gets bigger. And so we have the exact opposite happening that we had on the other side. Okay? And the same, or the symmetric concept would happen in the third quadrant. Between 0 and -1, it would be stretched out. But from 1 on, it's compressed closer to the x-axis. So it's important to understand, especially as we go into polynomials, and then as we progress next semester into calculus, if you take that course, it's important to understand what exponents do to numbers depending on where they were to begin with. So normally, when we raise the exponent, it lowers numbers between 0 and 1, and it raises numbers from 1 and greater. But if we use negative exponents, that process is inverted. Now, what would be different if my integers, my negative integers, were even? What would be different if I had y equals 1 over x squared? Would the branches of my hyperbola, would these arms that we have here, would they still be in the same quadrants? No. Somebody said no. Why not? What happens when we choose to apply a even exponent to x? What does that change? Let's think about it. We have 1, 1 here. When we had y equals, x to the anything, really. And we had, over here, -1, -1. What happens when I plug -1 in for x in this function? What's different? It just goes back to a positive. So what happens is that third quadrant branch gets reflected upward, essentially, because we're going to have a similar arm in the right-hand quadrant, in the first quadrant, it's going to be a little bit different than the other two because it's x squared. So it's going to be kind of between the red and the blue. But now we're going to have a branch in the second quadrant. And I'm not going to get too much into detail because I think we kind of get the concept of the powers and how they stretch it out. But that even number is going to bring it up. And of course, making it a higher and higher power is going to bring it closer to the x-axis in here, further away from the y-axis up here. All of the things that happen when we raise the odd exponents are going to happen. Now, let's just take a for instance. We've been looking at, well, let me see. Am I going to get to that? It's not mentioned there. So let's take a for instance real quick. We said that if we have something like y equals 1 over x, let's use to the 5th power. We're going to get something in the first and third quadrants. What if k is negative? Instead of having a 1 here, okay, what if we put in some different k that was negative? What would that change about our graph? All values would be reflected over the x-axis. Sure, if you were thinking all values would be reflected over the y-axis, that's true as well. You could go either way. What happens is, now, instead of having first and third quadrant arms, you would have second and fourth quadrant arms. Let's think about this. So let's use some specific points as an example. So suppose we started with y equals 6 over x. We know that we would have the points 2, 3, 3, 2, 6, 1, 1, 6, and all of the negative versions of those. And we'd have branches of our hyperbola that look roughly like this, because those are the points whose x and y values multiply to be 6. If I were to make that a negative 6, then in order to get numbers that multiply to be negative 6, the x and the y's have to have different signs. So I would have to have negative 2, positive 3, and negative 3, positive 2, and negative 6, positive 1, and negative 1, positive 6. Or 2, negative 3, and 3, negative 2, and 6, negative 1, and 1, negative 6. And so I get these branches instead if k is negative. Okay, I completely missed the points, but I think you get the point. And if we had an even exponent where both the branches were above, then when I throw a negative in there, they're going to both be below. It's going to flip them upside down. Are there any questions on this? On these integer powers? All right. So let's do a brief review of fractional powers. Algebra 2 actually covers what you do when your exponents are rational numbers. So we're going to just kind of go through it a little kind of briefly here. Fractional powers are actually demonstrations of the inverses of integer exponents, at least when the numerator of the fraction is 1 and the denominator is an integer. In other words, y equals x to the 1/2 is the inverse of y equals x squared. We normally read it as the square root, or radical x. Y equals x to the 1/5 is the inverse of y equals x to the 5th. And we would normally write it as the 5th root. And so since it's an inverse function, they are reflections over the line y equals x. If you take the line if you take the graph of y equals x squared and reflect it kind of obliquely over the line y equals x, you get y equals the square root of x. The problem is that if you do that with y equals x squared, y equals x squared is technically not invertible. It doesn't pass the horizontal line test that we talked about in chapter 6. And so in order to make that work, you have to restrict the domain of y equals x squared in order to make it invertible, which we'll look at here shortly. So the problem is that whenever our denominator, whenever our radical is an even, we can't take the square root or the 4th root or any even root of a negative number. If it's odd, 1/3, 1/5, or whatever, then we can. So suppose we had, in this case, y equals x to the 1/2. You can graph it a couple of different ways, or you can, the graphs are all going to be the same, but you can approach graphing it a couple of different ways. You can approach it directly by looking at it point by point. If x is 0, y is 0, because the square root of 0 is 0. If x is 1, y is 1. If x is 4, y is 2. When I'm graphing the square root function, I only put in numbers that have perfect square roots, that are perfect squares. So I would look at 0, 1, 4, 9, 16, so on. Just to make it easy on myself. So at 9 I get 3, at 16 I get 4, and at 25 I get 5. A little better. Now you'll notice that I don't get any of the negative numbers out. So the domain and the range are limited. What would be the domain for this function? What can I plug in for x? Let's see. I'll start calling on people using my calculator here. So Taylor at Alex Bay, what values can I put in for x? Okay. Well, let's look at it this way. Y equals x to the 1/2 is the same as y equals the square root of x. What can I not take the square root of? Negative numbers. So that gives me a limitation for x. So x can't be negative. It must be greater than or equal to 0. Now by this graph we can also see our limitation for y. What are we going to get out of this graph? So let's see. That's Copenhagen. They're not here. Still Copenhagen. Let's try. Nice. Paige at Sackett's. What are we getting out of this for y? Positive numbers again. Just be very careful that we also include 0. Normally, when we're writing our inequality, we remember that. But we have to remember when we say positive numbers don't include 0. Negative numbers don't include 0. 0 is the exception. So it's more precise to either say numbers greater than or equal to 0 or non-negative numbers. Non-negative numbers does include 0. Non-positive numbers include 0. Now, for really any power like this, for y equals k times x to the 1 over p. If k is positive and p is even, this is going to be your domain or range every time. So what happens if k is negative? We're going to continue with p is even, but if k is negative, imagine this function here as y equals negative x to the 1/2 or negative radical x. How does my graph change? No, she's not here either. Copenhagen. Eric, how does my graph change? The range becomes less than or equal to 0 because now whatever comes out of my square root, I multiply by -1 and it drops down below my x-axis. And so I get a nice mirror image of what I had on top. Okay, it begins to look like this. And so the domain stays the same because we haven't changed what can go in. We haven't changed what's under the radical, but we've changed it so that y is less than or equal to 0. Now, I want you to notice that our numerator is 1. Okay? If your numerator is not 1, that's going to change things, and we'll mention that later. See if we get to it today. It might be tomorrow. Let's just consider what happens now when p is odd. So as mentioned there in the notes, if p is odd, you can take odd roots of negative numbers. So if we have y equals x to the 1/3, that's the same as the cube root of x. And you can take the cube root of positive numbers. Okay, this is obviously going to be stretched. We still have 1, 1. Then we have 8, 2, because the cube root of 8 is 2. And then our next perfect cube is 27, and its cube root is 3. But you could take the cube root of negative numbers. Now, just in case you're rusty on why we can do cube roots and square roots, or we can do cube roots of negative numbers and not square roots of negative numbers, the cube root of negative 8 equals negative 2 because negative 2 to the third equals negative 8. You can't do that with squares. You can't square a number and get a negative number. It always comes out positive, so you can't take the square root of a negative number. So if our fraction has an odd denominator, what's our domain going to come out to be? Jamie, what x values can we use? Yeah, infinity. Any x number. It's going to keep going forever in both directions, left and right. So you can write that pretty much any way you want. You can write that as all real numbers. You can write that as an interval from negative infinity to infinity. If you want to get super fancy, you could use the symbols to say x is an element of the real numbers. So that stands for element of, and that's the symbol for real numbers. But yeah, any way you want to do that. It's usually on Wiley Plus. It's usually a drop-down menu, and you can put it however you want on the test. What about the range of this function? What is our range going to be, Joe? Yeah, it can be negative, it can be positive, it can be all of them. It doesn't look like it goes up forever and down forever. It looks like it kind of tapers off, but it doesn't. This will climb forever in both directions. So again, all reals or however you want to phrase that. We have to be careful with graphs like that because sometimes we do reach that tapering off point. We saw that with our hyperbolas earlier as it approached 0 in both directions. It might look like it keeps going, but we need to somehow draw our graph so it clearly shows that it kind of flattens off at 0 and doesn't cross it. So we'll get into the examples there tomorrow. Assuming we have school again, we'll see. We'll take a look at those tomorrow. And I'll get some homework up for you today. I know I said that on Thursday and I forgot to, but left myself a note. I'll get some homework up for you today. So we'll stop there, and everybody have a great day. If you have any questions, I can still hear you for a while. Feel free to ask me. Otherwise, we'll see you tomorrow.